You know, you sent in some pretty cool stuff about the Big Bang.
Yeah.
It feels like there is so much confusion about what it actually is, though.
A lot of baggage comes along with that term.
Yeah, it seems super straightforward, but like we're seeing articles saying that maybe it didn't happen at all, or that the
Mhm.
Webb telescope has thrown a wrench in the whole idea.
Hmm.
So we're gonna have to like break this all down,
Absolutely.
untangle it for you.
Yeah, and we're not here to argue for or against the Big Bang as like a monolithic entity or something.
Right.
Our mission here is to really dig into what scientists mean when they use that term
Okay.
and what the evidence actually points to.
Yeah.
We have Sabine Hossenfelder's article here, The Trouble with the Big Bang.
Yeah.
She does an excellent job of dissecting the core of this confusion.
Yeah, and I think that's what makes this so important because it's not just about semantics, you know?
Right.
It's like how scientists frame questions,
Yeah.
how they interpret new data. And it can lead to different avenues of research when you're thinking about the universe's origins and how it's evolving.
Absolutely.
So it turns out that the Big Bang isn't like this one straightforward concept.
Right.
It's more like an umbrella term
Yeah.
for different but like related ideas.
Hmm.
So we're going to break it down into 3 distinct meanings of Big Bang for you.
Okay.
So let's dive into that first meaning.
Okay.
And this is probably what most people think of
Yeah.
when they hear Big Bang,
Hmm.
at the very beginning of everything.
Right around 13.7 billion years ago.
The ultimate cosmic starting pistol.
Yeah, and this leads us to the Big Bang singularity,
Okay.
which is this point of infinite density and temperature.
So you're talking about when we run Einstein's theory of general relativity backwards.
Right,
Like
yeah.
to the very beginning.
To time zero.
Yeah. Okay, so this is where it gets really interesting.
Oh,
Physicists, they don't actually believe this singularity
hmm.
was a real thing that happened.
Right. They don't think it was a physically real state.
It's more like a general relativity,
Yeah.
which is really good at describing gravity.
It's our best theory of gravity.
Yeah, but maybe it just breaks down in these super extreme conditions.
Precisely. It's like our rule book for gravity stops working at that point.
Okay, so it's kind of like that analogy
Mm.
that Sabine Hossenfelder uses,
Well-
thinking about a water drop
Okay.
that's about to detach from a tap.
right.
And so mathematically, if you think of the water as perfectly smooth and continuous,
Hmm.
you end up with this singularity
An infinitely sharp point
right at that moment that it detaches.
at the moment of separation.
But we know that water isn't infinitely divisible.
Of course.
It's made of molecules. So
Hmm.
that singularity is just a result of the continuous description, ignoring the underlying molecular structure.
Right. It's an artifact of our description.
Yeah, and similarly, at these unimaginable densities of the early universe, we expect that the quantum nature of space-time itself is going to become really important.
Yes. And that's something that general relativity doesn't account for at all.
Okay, so that's where the Planck time comes in, right?
Yeah.
That incredibly tiny sliver of time
About 10:43 seconds,
after the singularity.
right after this hypothetical singularity.
And that's like the point
Yeah.
where these quantum gravity effects would be so strong.
They would just overwhelm everything else.
That general relativity would just not work anymore.
Exactly.
Okay, so physicists use this other term,
Yeah.
Big Bang event, which
Right.
is kind of a placeholder
Yeah.
for whatever kickstarted this expansion.
In a theory that would combine quantum mechanics and gravity.
And this is the theory that we don't have yet.
A theory of quantum gravity still eludes us.
Okay, so the Big Bang event is basically saying we don't know what happened at the very beginning.
Exactly. And importantly, we have no direct observational evidence for this Big Bang event.
Right.
Our earliest direct observation is the cosmic microwave background radiation.
Okay.
And that's about 400,000 years after the Big Bang event.
Right, so when you see that 13.7 billion years ago figure,
Yeah.
it's easy to think that the cosmic microwave background happened right at that beginning.
Exactly. And even a quick online search might give you a rounded number for the age of the cosmic microwave background. That makes it seem like it happened at the Big Bang, but it didn't. It's a really important distinction.
Yeah, so we actually have a pretty good understanding of the universe going back to about 10, 12 seconds before this hypothetical Big Bang event.
Right. That's what particle accelerators like the Large Hadron Collider can probe.
But that's still a huge gap
Right.
in energy density
More than 50 orders of magnitude in energy density.
before we hit that Planck time.
Exactly. A truly vast unknown territory.
And so it makes sense that there are all of these different ideas about how the universe actually began.
Right.
Like universes born from black holes or colliding brains.
That's from string theory.
Or even quantum fluctuations of nothingness.
Or cyclic universes with no true beginning.
Yeah, and so these theories exist because we can't see back to that time.
Right, they're attempts to describe what happened before the Planck time.
Right, and it's important to remember that the James Webb Space Telescope is not going to give us information about this Big Bang event.
Yeah, it's peering into a much later chapter in the universe's history.
Right, so it's looking at hundreds of millions of years after the cosmic microwave background.
Exactly. It's observing the formation of the first stars and galaxies, which is still really important.
Right.
But it can't see back to the very beginning.
So that was Big Bang number 1.
Okay.
Now let's move on to Big Bang number 2.
Okay.
Which is the expansion of the universe.
Right. And here we're on much more solid ground.
Yeah, this is like a fundamental cornerstone of modern cosmology.
It is, and it's supported by tons of evidence.
Yeah, and the story begins with Edwin Hubble, who observed that the light from distant galaxies was redshifted.
Right, so the wavelengths of light were stretched.
Which indicates that the galaxies are moving away from us. But as Sabine Hossenfelder points out, the decisive evidence for the expanding universe was the discovery of the cosmic microwave background radiation.
Right, that really solidified the idea.
Yeah, and that ruled out the steady state theory.
Yeah, the theory that said the universe was eternally the same.
Yeah, okay, so the cosmic microwave background is evidence that the universe was expanding and cooling from a hotter and denser state.
Precisely. It was like this afterglow of the hot early universe.
Right, so it's not direct evidence for a beginning event, like the singularity.
Okay.
But it is incredibly strong evidence that the universe has been expanding.
Yeah, and cooling.
Yeah, from that hot, dense state.
And the details of the cosmic microwave background, like its temperature, its uniformity, and these tiny fluctuations, fit perfectly into this picture of an expanding universe.
Okay, so we've covered the hypothetical beginning.
Yeah, Big Bang number 1.
Big Bang number 1, and the well-established expansion.
Big Bang number 2.
So now we get to Big Bang number 3, which is the concordance model.
Or, as it's also known, CDM.
And this is where things get really detailed, and maybe where some of the current debates are focused.
Absolutely. The concordance model is the best description that we currently have of how the universe is expanding and evolving.
And CDM stands for lambda.
Right, which represents dark energy.
Which is this mysterious force driving the accelerated expansion.
Exactly.
And then CDM stands for cold, dark matter.
Yeah, the invisible stuff that we think makes up most of the matter in the universe.
Right, and we think it provides like the scaffolding for galaxies to form.
Precisely.
So this model explains a lot of different observations.
It explains the cosmic microwave background, the large-scale structure of the universe, the abundance of different elements.
So it's like our best attempt to put all these pieces together.
Right, the rate of expansion, the way galaxies cluster all the different pieces of the cosmic puzzle.
Yeah.
And it does a remarkable job.
But it's important to remember that it's a model.
Yeah.
And it's not necessarily the only explanation.
Right. There could be other models that could also explain what we see.
Okay, so this is where the James Webb Space Telescope comes back in.
Okay.
And its findings are more about this concordance model than about like the initial Big Bang event.
Okay.
So we've been hearing about some early observations from Webb of early galaxies.
They seem a bit surprising.
They do seem surprising.
Yeah.
Yeah, because they seem bigger and more mature.
Much earlier in the universe.
Yeah, than the model predicts.
Than a lot of simulations based on the concordance model predicted.
So the standard picture is that galaxies form gradually.
Right. Within these halos of dark matter.
But if we're seeing these huge galaxies so early, it could mean that galaxy formation was more efficient than we thought.
And that could mean we need to adjust our understanding of dark matter.
Or other aspects of the model.
Right.
But Sabine Hossenfelder's article makes it clear that it's still early.
Yeah, the error bars on this early Webb data are significant.
Yeah, so we can't make any definitive statements about the concordance model yet.
We need more data.
And what's really interesting here is that this potential tension is about the model.
Right, Big Bang number 3.
Yeah, and particularly about dark matter and the formation of early structures.
Exactly. It doesn't challenge the fact that the universe is expanding.
Right.
And it doesn't say anything about the Big Bang event itself.
And that brings us to the core of the confusion.
Okay.
The fact that we use this one term, Big Bang,
Yeah.
to refer to 3 very different concepts.
Right.
The hypothetical, beginning the expansion that is definitely happening,
Mm.
and the model that describes that expansion.
It's a recipe for misunderstanding.
Yeah.
And even the Wikipedia entry for the Big Bang shows how imprecise language can add to this confusion.
Yeah, you might read about the Big Bang Theory, and it'll start by describing the expansion, then it'll mention the singularity,
Yeah.
and then jump to the evidence that supports the Big Bang. And it leaves you thinking that the evidence for the expansion is proof of that initial singular event.
Exactly, but it's not.
And then you have articles like Eric Lerner's "The Big Bang Never Happened,"
Right.
and his arguments gain traction because of this ambiguity.
Precisely.
And because people have trouble differentiating these three meanings.
Right.
So Lerner's critique is about the idea that the universe is expanding.
Big Bang number 2.
Yeah, so he says that different observations contradict this notion, but his interpretations of the data are different from what most scientists agree on.
Right.
So because there is this lack of clarity, when Lerner says that the Webb telescope data is challenging our model of expansion,
Right.
people might think it's evidence against the whole Big Bang concept.
Exactly, including the expansion of the universe.
And that's the problem.
Yeah.
And it's ironic that even articles trying to debunk Lerner sometimes define the Big Bang as the birth of the universe and link it to the cosmic microwave background.
Which just adds to the confusion.
So Sabine Hassenfelder says we need to be more precise with our language.
Absolutely.
So if we're talking about the stretching of space,
Yeah.
we should say the expansion of the universe.
Right.
Or if we're talking about a model, we should say something like the concordance model or CDM.
Yeah.
And maybe we should just use Big Bang to refer to that initial event.
Right. Or at least be very clear about which meaning we're using.
Yeah, because clarity is super important.
Absolutely. It would improve public understanding and make it harder for misinformation to spread.
Okay, so for you, the listener, the big takeaway from this deep dive is that there are these three distinct things that are often called Big Bang.
Yeah.
The Big Bang event, the beginning, that we don't fully understand. The expansion of the universe, that is definitely happening.
Right.
And the concordance model, which is our current best description of that expansion. Okay. And the James Webb Space Telescope's observations are about this model.
Right.
They don't provide evidence against the fact that the universe is expanding.
Or against the Big Bang event itself.
So as we continue to learn more about the universe with tools like the James Webb, what might we find out about the very beginning?
Right.
And how our language need to change to reflect that? Think about how different the evidence is for the expansion compared to our theories about the origin.
Right.
It's a really fascinating frontier.
Absolutely.
Thanks for joining us.
It's been a pleasure.